Buon pomeriggio, benvenuti a questo incontro di Biennale Tecnologia. Sono Juan Carlos De Martin, uno dei due curatori di questa manifestazione insieme a Luca De Biase, ma questa volta, in questo momento, il mio ruolo è quello di introdurre il nostro ospite d'eccezione e poi, dopo la sua lezione magistrale, di gestire l'interazione col pubblico, perché sapete che tutti gli incontri di Biennale Tecnologia ci abbiamo messo l'impegno di mantenere sempre almeno 10 minuti, 15 minuti, 20 e in molti casi è stato anche ben di più di interazione col pubblico, cosa che è avvenuta siamo ormai quasi alla fine, posso dirlo, è avvenuta praticamente sempre con grande soddisfazione di tutti. Ho sentito ormai molti relatori felici di questa interazione con un pubblico che hanno descritto come attento, qualificato, quindi un pubblico di Biennale particolarmente notevole. Allora, sono qui a presentarvi la nostra ospite, la professoressa Naomi Oreskes. Vi dico direttamente subito i titoli. Lei è Henry Charles Lee, professor di Storia della Scienza dal Dipartimento di Storia della Scienza dell'Università di Harvard, e sono particolarmente contento e la ringrazio di aver accettato di fare questa lezione magistrale, purtroppo online per esigenze della professoressa, ma speriamo magari di averla anche in futuro, magari già dalla prossima edizione in presenza qua a Torino. Sono molto contento perché la professoressa Oreskes è uno dei più importanti studiosi del tema del rapporto tra tecnologia, scienza e società. È una studiosa che ho incontrato anche nel mio personale percorso di studi, perché quando lavoravo sul mio lavoro sull'università, che è uscito nel 2017, avevo incontrato un libro che effettivamente è uno dei grandi libri su questi temi di questo inizio di XXI secolo, che è Mercanti di dubbi del 2010, Merchants of Doubt, dove Naomi Oreskes, insieme a un coautore, illustra, documenta concretamente come una strategia fondamentale per ritardare determinate azioni normative importanti per il tabacco, per il riscaldamento climatico, eccetera, siano state strategie potremmo chiamarle di disinformazione scientifica, di incentivazione, disseminazione di dubbi che poi venivano usati per ritardare azioni normative, leggi, regolamenti ampiamente necessari per la salute pubblica, per il bene pubblico. Quindi lei si occupa di storia delle scienze ambientali, di politica della scienza, dell'area di studi chiamata Science and Technology Studies, appunto tecnologia e società, e ha pubblicato come autrice o come coautrice 9 libri e più di 150 articoli. Non starò ovviamente, per questioni di tempo, per non togliere tempo a lei che è il vero ospite, a elencarveli tutti. Ha curato l'introduzione, questo lo trovo interessante, dell'edizione della Melville House in inglese di Laudato Si, l'enciclica papale sul riscaldamento climatico e sulla disaguaglianza, e poi vedo che sta lavorando a un nuovo progetto di un libro che è previsto in uscita tra poco, nel febbraio del 2023, quindi effettivamente potrebbe essere un'ottima scusa per invitarla nell'edizione 2024, intitolato Il grande mito, come il business americano ci ha insegnato a trovare, negativo il ruolo del governo e amare il libero mercato. Ma il motivo per cui è qui, e anche il titolo di questa lezione, è che il libro, l'ultimo che è uscito nel 2021, pubblicato anche in Italia da Bollati Boringhieri, che ringrazio per la collaborazione, è il libro Perché fidarsi della scienza. Perché fidarsi della scienza è veramente un libro legato a quello che è capitato in questi ultimi 2 anni a tutti quanti noi, e quindi un libro in cui argomenta, consapevole di cos'è la scienza veramente, quindi non quella caricatura manichea che spesso abbiamo sentito presentata nei media italiani, e forse non solo italiani, in questi 2 anni, quindi consapevole che la scienza è una cosa complessa. Perché comunque fidarsi della scienza? Cosa vuol dire fidarsi della scienza? Quindi ci sembra un tema assolutamente d'attualità, vale per i discorsi sulla pandemia, vale per il riscaldamento climatico, vale per moltissimi altri temi che ci riguardano tutti quanti, riguarderà le generazioni future, e quindi con grandissimo piacere do il benvenuto alla professoressa Naomi Oreskes e le cedo in questo caso lo schermo per la sua lezione magistrale, che io seguirò in prima fila. Grazie.
Thank you very much. Yeah, I can hear you, can hear me, so that's great. So thank you for that kind and generous introduction, and I definitely hope to come to Italy in 2014. The new book is called The Big Myth: How American Business Taught Us to Loathe Government and Love the Free Market. And it really picks up on questions of propaganda and disinformation that we argue stand in the way of appropriate action on climate change and many other issues. But today I want to talk to you about my book, Why Trust Science? And I thought I would start by just saying a few words about why I thought it was important to write a book about trust in science. The first reason is that back in the 2000s, even before Merchants of Doubt was published, I gave many public lectures about climate science and global warming. And I often found that after I would give these lectures, in which I explained in great detail the history of climate science, how scientists had come to understand that global warming was happening, sometimes people in the audience would say, well, that's all very well and good, but why should we trust science? And I think when people would say this, it made me realize that it's not enough for us to simply say, trust us, we're experts. Our audiences deserve an answer to the question, an explanation for why science deserves our trust, if indeed it does, and maybe why at times it doesn't. And as you just heard in the introduction, not a caricature, not a cliche, but an actual serious discussion of what is a really important issue. The second reason has to do with scientific uncertainty. The fact is, we can't say that science is absolutely true because science is a process of learning and discovery. And like all human enterprises, it is fallible. Scientists do make mistakes. And so no matter what we do, we can never say that something has been proven in an absolute sense. And so this raises a serious question about how to understand the significance and reliability of current understandings and why we should trust science, even though we know that sometimes in the past scientists have gone wrong. The third reason comes from having written Merchants of Doubt, which you just heard about, a book about the deliberate generation of public mistrust and distrust in science by the people we call merchants of doubt. The major finding of that research was that the tobacco and other industries had deliberately tried to create public distrust in science that showed the damaging effects of their products, but then also generalizing this to try to make citizens and consumers distrust science in general because these companies came to see science as their enemy because science was telling the truth about their dangerous products. And then, of course, more recently, the current political situation in the United States and elsewhere. Not too long ago, we had a vice president who was a young Earth creationist who publicly said that he believed the Earth was only 6,000 years old. He also had written pieces saying that he did not believe that tobacco caused smoking. So this is obviously very troubling. And so for all these reasons, and probably some more, it seemed to me important to take on this question, to take it seriously and try to provide an answer that was not a caricature. There was just the example of Mike Pence's op-eds about claiming that smoking doesn't kill. And then, of course, in the last 2 years, we've experienced the COVID-19 crisis, and we've seen how rejection of science has literally become a matter of life and death. In the United States, more than 1 million people are now dead from the COVID-19 disease, and a study by the Lancet Commission concluded that about 40% of those deaths probably could have been avoided if people had paid attention to scientific advice, accepted masking, and then when they were able to, got vaccinated. So it's not just an academic issue. We live in a moment when trust in science has literally become a matter of life and death. So let's start with the issue of scientific uncertainty. When I think about scientific uncertainty, I like to start with the work of Blaise Pascal, the great French mathematician and philosopher who made many important contributions to science, but thought the most important question of all was the question of the existence of God. Pascal posed what today we would think of as a type 1 versus type 2 error. He asked the question, what are the relative risks of believing in God if God does not exist versus not believing if God does? One only has to think about this for a minute. If you do believe in God, but it turns out there isn't actually God, then not much is lost. But if there is a God and you don't believe, then, according to Christian theology, you will burn in hell forever. And so Pascal concluded that it was definitely better to believe. In other words, it's about the consequences of our belief, the consequences of accepting or rejecting scientific knowledge. So what Pascal developed was what philosophers would call a consequentialist framework. And we can compare this to the alternative, which is a nomological framework like the Ten Commandments. So we can evaluate things according to a set of preordained rules, or we can evaluate things according to the consequences. So put this in secular terms, we can say that you might not need it, but it's safer to hold the handrail. Now, this discussion of Pascal and God might make some people uncomfortable because it might make it sound as if science is a leap of faith. And sometimes it can seem so. The reality is that most people, even really most academics, have no idea how to judge whether scientific claims are true. Even many academics may not know how to judge claims in areas outside of our own expertise. But like Pascal, most of us assume that the risks of accepting scientific claims are generally smaller than the risks of rejecting them. But should we do this? Should we trust science? And if so, why? What is the principled argument for confidence in scientific conclusions? Well, the traditional answer to this is the scientific method. That is to say, the traditional answer is to say that scientific answers are correct because scientists use a method, the scientific method, that guarantees the accuracy of the results. Typically, this is referred to as the hypothetico-deductive method, and I'm sure all of you have heard of this. The idea that we develop a hypothesis, we deduce its consequences, and then we see if those consequences are true, and if they are, we're happy and off we go. And if they're not, then we revise the hypothesis. Now, scientists do sometimes do this, and we have some very famous examples in the history of science. For example, when Albert Einstein proposed this theory of general relativity, which proposed that starlight would be bent in the presence of a massive object, this led to the prediction, well, as I said, the prediction of the bending of starlight. An experiment was done to test that prediction, and lo and behold, it turned out to be true. Now, sometimes academics will call this the deductive nomological model, because academics always like to use fancy words when simple ones will do. But there's also a reason, nomological, because in the ideal case, we aren't just developing a specific hypothesis, we're searching for the universal laws of nature, like E equals mc squared. The problem with the hypothetical deductive model is that as a logical claim, it doesn't work. And it doesn't work because of something that philosophers call the fallacy of affirming the consequent. Just because a prediction turns out to be true does not, in fact, prove that the theory that made the prediction is true, for the simple reason that false hypotheses can actually sometimes make true predictions. So if we go back to the 15th and 16th century, we know that the Ptolemaic system of the universe placed the Earth at the center of the universe, a claim that today we would all say is incorrect. But this theory made highly accurate predictions of the motions of planets, the timing of eclipses, and other things. In fact, it was more accurate than the Copernican model when the Copernican model was first proposed. The second reason that the theory of the hypothetical deductive model doesn't work is the problem of auxiliary hypotheses. What that means is that when we test a hypothesis, we're not actually just testing that specific hypothesis. We're also testing various assumptions that are built into the test. We're also testing the reliability and sensitivity of our instruments. So we can look at a close example of that. So when Copernicus proposed that the Earth was not the center of the universe, that actually the sun was the center and that planets moved around the sun, people said, well, okay, if that's true, if the Earth moves, we should be able to detect effects of that motion. One of the effects was the phenomenon known as stellar parallax, the change in the apparent position of stars as the Earth moved through its orbit. So you can imagine looking at a very bright, distinctive star in December, you would see it against a particular backdrop of stars, but look at that same star come June, and it would appear against a different backdrop. So astronomers in the 17th century looked, and they found nothing. Now, according to the hypothetical deductive model, those astronomers should have rejected the Copernican theory. They should have viewed it as falsified, to use the language of Karl Popper, and they should have stuck with Ptolemy. And yet, Few of us would argue that that's correct. So what's going on here? Well, in hindsight, we can see that there was a strong auxiliary hypothesis at work. Scientists were assuming that the Earth's orbit was large relative to the distance to the star that was being observed. In fact, we would now say today that the Earth's orbit is tiny, tiny, tiny compared to the distance. And so the stellar parallax is extremely tiny. And therefore, they had a wrong assumption about the scale or the magnitude of the effect they were looking for. Put it another way, we could say they had the auxiliary hypothesis that their telescopes were sensitive enough to detect the effect. In fact, telescopes did not detect this effect until the work of Sir William Herschel in the 19th century. So we might say that the hypothetical deductive model is an oversimplified model of the or an oversimplified picture of the scientific method. And in some ways that would be fair. But the problem is that a good deal of science simply doesn't follow the hypothetical deductive model. That is to say, the model is not an accurate description of what scientists actually do. A good deal of science is inductive. Induction is the process of generalizing from observations. And some of the most important work in the history of science was inductive. The most famous example is Sir Charles Darwin. As most people, if you've read a biography of Darwin, you know that when he went on the voyage of the Beagle, he had no theory. He was not testing a theory. He simply knew he needed a job and he didn't want to be a doctor. It was only many years later, after he had collected huge amounts of data, that he began to develop those data into the theory of evolution by natural selection. So in induction, observations come first. Another form of scientific practice is modeling. Sometimes we see things in the world and we don't know how to explain them, but we make a model and we see if we can reproduce the phenomenon with that model. And if so, say, well, then this might be the cause. So in the 19th century, a very significant question for geologists was the question of the origins of mountains, and particularly the big folds that were sometimes seen in the European nappes, folds in which it looked as if the rocks had behaved as if they were soft like clay and as if they had been pushed from the side. And so this man, Sir Henry Cadell, made a physical model to show that, in fact, you could produce those kinds of effects by compressing rocks from the side. Now, nowadays, most people don't make physical models. Most of the models that scientists work with today are numerical simulations. The point of this discussion is not to say that any one of these approaches is right or wrong, but simply to point out that there are many different scientific methods, that at different times in history, in different places, in different fields, scientists have preferred different methods. They choose the method that seems to work for the problem at hand. Because the methods of science are so diverse, the philosopher of science, Paul Feyerabend, once said that the method of science was, quote, anything goes. Well, he didn't actually say that. The longer question or the longer quotation was in response to a question. Feyerabend said, well, if you were to press me to say what the method of science is, I would have to say the only principle that does not inhibit progress is anything goes. So Feyerabend was not saying that, in fact, anything goes really. What he was saying is that the methods of science are diverse, that scientists are innovative and creative, and we choose methods that work for the problem at hand, or that we prefer for various reasons, some good, some not so good. And in my first book, The Rejection of Continental Drift, I have a big discussion of why scientists, American scientists, had different opinions about scientific method than their European colleagues, and how this influenced whether they thought continental drift was true or not. And I can tell you, since you're Europeans, that actually the Europeans were right. Now, the point is that different problems can call for different solutions. So this leads to the question, do any of these diverse methods then have anything in common? And I have argued, and argue in my book, that what all these different methods have in common, what unites the diverse forms of science, the different disciplines, geology, physics, chemistry, and also the social sciences, psychology, anthropology, sociology, is not a common method, but a common attention to evidence. These different methods are all means of collecting, generating, and creating evidence. Scientific claims are claims that have been supported by empirical evidence. So I argue that evidence is actually the key element in scientific knowledge, not method. And so if we have a question like the efficacy of vaccines or the reality of global warming, the key thing is not to ask, what method did the scientists use or which scientists are saying this. The key question to ask is, well, what is the evidence? How much evidence is there? And is the evidence robust? Is it diverse? Has it been collected by many different people? So that if any one person is making mistakes, we have evidence from other labs, other teams. But of course, this raises yet a new question. Every answered question in academic life begets a new question. So the question is, well, who judges the evidence? And the answer, of course, is scientists. So then we have to ask, well, so how do scientists decide when they have enough evidence to say that something is known, that something is proven, that something is a fact? And this is what has led me and other scholars to focus on the question of scientific consensus. Now, there are some people who don't like scientific consensus. They think it's not robust enough. They don't think it's tough or something, or they think it's that we're saying that science is just a matter of opinion. But if you actually look empirically, that is to say, if you take the question of scientific method as a scientific question and you look at the evidence, what you find is that scientific knowledge is the body of claims that have been agreed upon by trained experts. Claims that those experts have concluded are supported by sufficient evidence to say that the claims are true. Or put another way, scientific knowledge is the body of claims about which experts have come to consensus. Now, as I said, this troubles some people for a variety of reasons. And one reason it troubles some people is that it appears to be an appeal to authority. And traditionally, most of us have been taught to believe that the appeal to authority is a logical fallacy. Well, in some ways it is. But it's a particular kind of authority. It's not the authority of an individual genius, no matter how brilliant or wise. We don't believe in the theory of relativity because of the genius of Einstein. We believe in relativity because of the collective authority of diverse evidence, people other than Albert Einstein who weighed and judged the available evidence. And this is not just true for relativity theory, this is true for all scientific theories. The person who proposes the theory is in the end not the judge of it. The judge of it is all of his or her colleagues, all of the other people involved in the scientific conversation. And very often the evidence to support a theory may come from different people than the person who proposed the theory in the first place. So in my book and elsewhere, I've argued that science relies on the collective scrutiny of claims. The fact is that we're all rather poor at identifying our own mistakes, but happily, we're quite good at identifying other people's mistakes. Science capitalizes on this cognitive reality, and it uses it to identify and correct error. So when we talk about science being, quote, self-correcting, this is what we're really talking about. It's not really that science as an abstract concept corrects itself. It's that scientists challenge and correct each other. Now, science is an abstract concept, of course, and a concept couldn't possibly correct itself. But science is also a human enterprise composed of people we call scientists. So as I've just said, science doesn't correct itself, but scientists do correct, sometimes themselves, but mostly they correct one another. The philosopher Helen Longino has called this transformative interrogation. It's interrogation because it's tough. Science is not easy. You have to be thick-skinned. Often your colleagues can be pretty mean, sometimes even nasty. But it's transformative because what survives at the end is typically not the same as what was claimed at the starting point. Scientists adjust their claims in light of critical scrutiny. Sometimes they go back and collect more data. Sometimes they conclude that the original idea was simply no good. And occasionally they revive their thinking entirely, and this is what we refer to as paradigm shifts or scientific revolutions, as when the Copernican theory did displace the Ptolemaic model of the university, or continental drift was accepted, displacing static theories of the Earth, or relativity theory displaced Newtonian mechanics. So to the extent that scientific knowledge is reliable, I argue, is because it has withstood this tough process of critical scrutiny. And to the extent that it's objective, it's because it has survived this intersubjective analysis. That is to say, it's not simply because I, as an individual, are so superior that I can be objective. It's rather, as Helen Longino has argued, the objectivity of individuals in the scheme consists in their participation in the collective give and take of critical discussion, and not in some special relation of detachment, hard-headedness that they may bear to their observations. Thus understood, objectivity is dependent upon the depth and scope of the transformative interrogation that occurs in any given scientific community. In other words, to put it in plain language, what we call scientific facts are simply claims that have withstood this tough critical expert scrutiny. And this brings me to the importance of diversity in science. The processes of transformative interrogation are most likely to work well when a scientific community looks at a problem from a variety of angles. And that is more likely to occur when the community is diverse than when it is homogeneous. To understand this claim, we have to talk a little bit more about objectivity. Many people think that science works because scientists as individuals are objective. And certainly it's true, I think, that all good scientists try to be objective. We can say that objectivity is what philosophers call a regulative ideal, something we strive for. But most people still think of objectivity as a characteristic that is inherent in individuals. So sentences like, I am objective, or she is not objective, or a good scientist is objective, these sentences seem to make sense. But various scholars, cognitive scientists, linguists, philosophers have said, well, not so fast, because the opposite of objectivity is not bias. The opposite of objectivity is subjectivity. And the fact is, we are all subjective because all perception is subjective. It's conventional to compare objective facts with subjective opinion. So, for example, an objective fact, The Force Awakens is the highest grossing Star Wars movie. A subjective fact, The Empire Strikes Back is the best Star Wars movie. Or this comparison, these are oranges, I love oranges. The problem is that that doesn't actually solve the problem, because different people can look at the same objective reality and see very different things. So if we go back to this example, well, are we actually sure that those are oranges, not tangerines or satsumas or clementines? Or maybe they're plastic fruit. Or here's my favorite example. Is it a 6 or is it a 9? The reality is that people, even highly trained experts, can see the same things in different ways. And it's not a matter of objectivity versus subjectivity, because on some level, we all are subjective. Or as the Bayesians would say, we all bring our priors to a question. We see things from our perspective and evaluate them according to our experiences, our values, our preferences, our habits. And it doesn't make us bad people or even bad scientists. It just makes us human. So think about the classic example of the blindfolded people and the elephant. Each correctly perceives a portion of the creature, but because their perspectives are incomplete, they come to incorrect conclusions. A scientific community that is homogeneous may tend to look at that elephant in the same way, and therefore are more likely than a heterogeneous community to miss aspects of a problem or phenomenon that may be important. And in my book, I give some examples of episodes in science where in hindsight, we would say that the scientific community did get it wrong. And one of the common features we see in many of those communities is that they were very homogeneous. And in some cases, we see that because the diverse voices were minorities, those voices were ignored. So what I would argue is that many past errors in science, that is to say, things that in hindsight we identify as errors, can in fact be attributed to communities that were not diverse, and had significant blind spots, or where there was informed internal dissent that was brushed aside. And so this brings me to what I think is perhaps the most important point of my work on this question, that diversity is not just a moral value, it's an epistemic value as well. That is to say, it helps us get the right answers. We shouldn't trust the opinion of just one person or jump to conclusions based on a single study. Science is a collective project, and evaluating evidence takes time. Sometimes new evidence may lead us to reconsider old views, and this is what we traditionally call progress. But until such time as there is new evidence, our current knowledge is the best basis for reliable decisions on issues like climate change that hinge on scientific information. And I want to say this again because I think this is something that has really been missed by a lot of the media in recent years. Of course, we will learn more in the future. We want to learn more. We hope to learn more. But that's not an excuse for rejecting or ignoring or dismissing what we think we know today. And if we look at the history of science, we can still see that often scientific evidence did form the best available basis for decision making at that time, even though in the future scientists may have revised their views. So to conclude, why should we trust science? Well, the short answer is because of its track record. That track record can be attributed not to a single scientific method, but to the shared processes of critical scrutiny of evidence, which over time may lead to scientific agreement, what we conventionally call scientific consensus. Scientific knowledge is not based on geniuses. There have been geniuses in the history of science, but if we had only relied on them, we would know rather little about the natural world. Science, as we know it, is based on many people working together. And it works because of the accumulated expertise and experience of these people. And it works best when a diversity of perspectives have been brought to bear on the question at hand. Put another way, we should not trust scientists as individuals, but we do have good reason, both historically and philosophically, to have confidence in the process of which they are a part. And then there's one more consideration. If we return to Pascal, we can ask the question, with respect to any particular problem, what are the relative consequences of accepting the scientific claims if they turn out to be false, versus rejecting the scientific claims if they turn out to be true? When it comes to climate change, the issue that I have worked on most closely over the past 20 years, if our scientists are right, but we ignore their findings, the consequences are likely to be dire. If, on the other hand, it turns out to be a big hoax, well, then we will have created a better world for nothing. Thank you very much for your time.
Grazie molte alla professoressa Oreskes per questa sua lezione e abbiamo un po' di tempo, direi sì, almeno 20 minuti per dei interventi concisi e possibilmente delle domande, perché abbiamo questo privilegio di avere la professoressa Oreskes collegata con noi, quindi approfittiamone per porgerle delle domande. Ci sono dei borsisti in sala con dei microfoni e quindi se qualcuno vuole fare una domanda alzi la mano, le verrà recapitato un microfono. Qui c'è una prima mano alzata, grazie.
Hello, Professor. Thank you very much for your lecture. It was very interesting. I have one, I think is more of a personal question. How do you deal with the anxiety of knowing that there are people that are actively denying scientific facts and they are in positions of power, also that there are many people that are actively on their everyday lives making decisions that are potentially bad for the rest of us?
Thank you. That's a great question. I would say the main way I deal with anxiety is through action. I think that when we act to try to push back against those forces of disinformation, it may not solve the problem overnight, but it does help to deal with the anxiety because at least you feel that you are doing what you're able to do. And so much of my work is really about exposing bad actors as bad actors We say in English, mold grows in dark places. So if we can shine a light on disinformation and where it's coming from and what the motivations are, I think that helps people to see that this is disinformation and that they should not believe it. And that, in a way, answers your second question as well. In terms of ordinary people, I don't see ordinary people as bad people. I think that many people are confused because they have, in fact, been victims of disinformation. And so if we can give them good information and explain what has been going on, then we can empower those people to make better choices.
Hello. My question is about, it should be about climate change, because I remember we had a very nice lunch together at the Vatican discussing this question. But the immediate problem, which should be a scientific one, but is not regarded as a scientific question for an English person today, is this crazy Brexit thing going on, which is one of the reasons why I'm now in Italy. But the question ought to be put to all the people, ought to have been, is it in the economic interests and interests of Britain to be able to leave the European Union? And the evidence, which was brushed aside, as you said, was that it was not in those interests, but it went ahead anyway and can't be now reversed. So is the question of how science operates related to the question of how human beings operate in the real world, where science is not the basis for decision making?
Thank you. That's a great question, and nice to see you again. I think you raise an extremely important point, which is that the issues that I'm talking about and writing about, I focus on science because I'm interested in science. I was trained as a scientist, and because we have these very key current issues, such as climate change, which depend on scientific knowledge and information. Science doesn't tell us what to do about it, but it does tell us that we have a real problem that needs to be addressed. But as you suggest, the importance of facts, the importance of information goes beyond questions that we would see as strictly scientific. And certainly in the case of Brexit, it's pretty clear that a lot of disinformation was promoted around the Brexit debate. And so I think that one of the reasons this conversation that we're having here right now is so important is that we need to develop a toolkit to help expose disinformation, whether it's about a scientific question or an economic question. And I mean, of course, we have colleagues who would say economics is a science. I don't want to go there. But to find ways to identify disinformation, to name and shame it. And fortunately, we do have colleagues who are doing some good work on this, particularly my good colleague, John Cook, who has been working on what he calls inoculation. So his studies show that if you give people good scientific information, and then you also give them disinformation and ask them, well, what do you think? Most people will just be confused. But if you give them good scientific information and then you say, but the problem is that there's actually disinformation out there, and the people who are promoting the disinformation are motivated by money or ideology or whatever it is, and then you give them the disinformation, it's as if you've inoculated them against the virus of disinformation. That's a really important finding because in my experience, most scientists think that the solution to these problems is simply to give people more science or to give them more facts and more economic facts or more statistics about, the benefits of being part of the European Union. But all of our available evidence, both scientific and day-to-day life, tends to suggest that that doesn't work. But if you show people that they're being lied to, if you show people that they're really being the victims of disinformation, most people do not want to be the victims of a con. Most people do not want to be on the losing end of a con game. And so I have found that when I talk to people about this and when I explain that this really is a kind of a con game, and that in the case of climate change, the fossil fuel companies are laughing all the way to the bank, making giant profits while we're picking up the bill for climate damage, that for many people is eye-opening. And it's very different and has a much greater effect than if you simply gave them more evidence from climate models or more evidence from ice cores or whatever.
Lei ha parlato della comunità scientifica e la comunità scientifica ovviamente per motivi di tempo l'ha presentata come se fosse qualcosa di omogeneo. A cosa faccio riferimento? Faccio riferimento al fatto che la comunità scientifica in alcune discipline, in particolare penso per esempio all'economia, ma alcune altre discipline, non è effettivamente rappresentativa della comunità mondiale di ricercatori, ma è fortemente, come dire, condizionata, influenzata e anche proprio veri e propri centri di potere, le riviste più prestigiose, le associazioni più prestigiose di determinati paesi, in particolare gli Stati Uniti. Quindi da questo punto di vista la comunità scientifica, quella che lavora col processo che lei ha descritto per raggiungere un consenso, è una comunità scientifica che, ripeto, in alcune discipline più che in altre, ha un bias, ha un orientamento che le porta inevitabilmente a avere sensibilità, valori, obiettivi, priorità che non sono necessariamente quelli, per esempio, del Latino America, dell'Africa o dell'Asia. Allora, da questo punto di vista, lei a un certo punto ha parlato anche di diversità, forse anche di inclusione. Non pensa che un passo in avanti importante nel perché fidarsi della scienza potrebbe proprio anche essere dimostrare concretamente nell'attività delle associazioni scientifiche una maggiore pluralità, una maggiore attenzione a priorità, culture e valori effettivamente molto diverse da quelle tipicamente anglosassone o europee continentali?
Yes, thank you for that question, which is really, really important. And you're right, I probably in my talk should use the word communities, plural, rather than community. But you're absolutely right, and you raise an extremely important point, that very often our scientific communities are not very diverse. They're probably becoming more diverse in Europe and the United States than they were 20, 30 years ago when I began my scientific career, but there's still a dominance of voices from what we conventionally call the global north. And this is a very important problem because we know, and this is part of my argument, that when people come to a problem with different life experiences, they will see the problem differently. And they will often notice evidence that other people have not noticed or have discounted or sometimes just eliminated completely. And so it is extremely important to think about strategies to embrace and accept those voices. So there's two things that I've written about, if I can make a shameless plug for another one of my books. So last year I published this book that I've been working on for many, many, many years called Science on a Mission. And it looks at the impact of funding structures on research in the field of oceanography. And it's a very detailed study of one particular science in one particular time period. So this is American oceanography during the Cold War. And it's 500 pages just on that one science because it's difficult to prove that the funding structures influence the scientific results. Because many scientists believe, they believe in an objective reality. They believe the purpose of science is to find the truth about that objective reality. And therefore, they don't think it matters who pays for the science because if we do science objectively, we'll find the true results. But I think the evidence does not support that hypothesis. And I think there's a few different reasons why, and you'll have to invite me to come to Italy and spend a whole weekend talking about these things. It's not easily reduced to a soundbite, but one of the points I make in the book, though, is that actually it does make it. And to show that, to demonstrate that, requires digging into the science with a degree of detail that is hard to do. So it takes a lot of time to be able to prove this case. So I feel that I have done it here for the issue of funding. And so one of the arguments I make in the book is that it's quite important for funding sources to be diversified. And I believe it's a big mistake when universities say, oh, it's fine if we get all our money from the private sector. I think that it's really important for us to argue for the continued commitment of governments, of foundations, of private philanthropy. And yes, the private sector in some cases is a good funder of science, but a diversity of funding sources is really crucial to ensure that we are looking at a diversity of problems and in a diversity of ways. Now that's just about the money piece. Your question also points to an even deeper issue, which is the diversity of the people involved. That, again, is a hard thing to prove, but we do have good evidence, particularly from feminist historians and philosophers of science, So 2 books that I can think of, Londa Stiebinger, the American historian of science, has done very extensive work looking at what difference it makes when women become involved in science, in sciences that didn't have women before. And he has many examples where you can see that when women join the conversation, new ideas are introduced, new hypotheses. It really has changed what scientists think is the truth about questions like human evolution, for example. Another example comes from mathematics. You might think mathematics is impervious to social influence because human evolution is one thing. Of course, we have biases about ourselves, but math is math. But Claudia Henrion, in her book, The Addition of Difference, shows how when women became more present in mathematics, it changed mathematics as well. So we have good evidence about funding structures. We have good evidence about the impact of women in science. We don't have as much good evidence about these other pluralistic questions, but I think it's extremely important. And I'll just share one other thing because maybe I can shame the IPCC a little bit here. A few years ago, a group of us wanted to study the IPCC process to understand how they came to the consensus conclusions reported in their report. And one of the things we wanted to look at was the question of how well the scientists from the global south were being heard in this process. So we know that the IPCC, to its credit, and I want to give credit where credit is due, has really made an effort to develop author teams that are diverse, that include both men and women, and people from both the global north and the global south, including from countries that don't have well-developed scientific infrastructures. And I think they've done this because they recognize that it matters. Like the fact that the IPCC has adopted this pluralistic framework, I think is proof that scientists themselves do recognize that scientists from the global south and elsewhere bring really important perspectives to the table. And yet, when I spoke to people in the hallway, off the record, many of the scientists from the global south, particularly women, said that although they were present at the meetings, they didn't necessarily feel that they were being heard. And so one of the key questions is, how do we ensure that it's not just window dressing, that we're not just performing diversity, but we're really taking these alternative views seriously? The IPCC would not agree to let us do that study because they feared that if they let outsiders into the process, that it would somehow disrupt the process. I think that fear was unwarranted and unjustified. We've done studies like this in other places, and people have felt comfortable with the results that we came up with. So I hope the IPCC will rethink that, because I think it's a crucial question that's relevant not just to the IPCC, but to all of science.
Grazie molte, mi viene in mente un politico americano di cui adesso mi sfugge il nome, che diceva non c'è bisogno di controllare la scienza direttamente, basta controllare la fonte di finanziamento, e i grandi progetti scientifici hanno bisogno di tanti soldi e quindi è decisivo per poterli influenzare.
Buonasera, grazie della lecture. La mia domanda è legata a degli aspetti che sono già stati discussi in parte. Ok, la disinformazione, ok, la misinformation. Questi sono ovviamente dei problemi concreti e di cui si è, diciamo, consapevoli. Ma la questione che penso sia importante è come migliorare la comunicazione della scienza e del metodo scientifico. Questo penso che sia una questione rilevante, visti i nuovi mezzi di comunicazione, e penso che la scienza possa in questo modo riflettere a come si presenta, soprattutto nelle società aperte, democratiche, dove ci sono diversità. Anche nella stessa comunità scientifica ci possono essere state posizioni differenti che hanno portato magari confusione nel comprendere in un momento di difficoltà e di pericolo. Quindi la mia domanda è: come si può migliorare la comunicazione scientifica nel mondo tecnologico di oggi? Grazie.
Thank you for that question. It's a great one. In a way, it makes me laugh a little bit, because when I first started this work, almost everyone I knew, all the scientists I knew, all thought that what they were facing was a problem of communication. And so a lot of scientific societies, particularly here in the United States, started developing programs in scientific communication, some had workshops, sometimes even required students to take a course in communication. And while I agree that scientific communication is extremely important, one of the points I was making, if we go back now 10 or 15 years, was to say, well, wait, hold on, this is actually not a problem of scientific communication, this is a problem of disinformation. Because in the climate community, we were facing outright disinformation, and the scientific community was not aware of it at that time, and their responses were proving ineffective because they weren't accurately diagnosing the challenge that they were facing. So you raise a really important point. How do we even know whether what we're facing is information, disinformation, communication? And I think your question correctly points to the fact that we have to be mindful that at any given moment, the challenges can be different. And so certainly in the last 2 years, certainly with the COVID-19 pandemic, and I assume that might be in part what you're thinking of, we saw a lot of really bad science communication. And we definitely saw people being confused by scientists saying things that in many cases were not helpful. So what do we do with that? I think the most important thing that came out of the COVID-19 pandemic in terms of science communication was the importance of being able to say, we don't know. And this is a very hard thing for scientists because many scientists feel they're supposed to know, but they get paid to know. And especially if they get a phone call from a journalist or they're asked to appear on television, they may feel compelled to say something. And I've actually heard scientists say this, well, we have to say something. I actually think that's incorrect. I don't think we have to say something, or at least we don't have to pretend we know. We should not pretend we know when we don't. So in the case of COVID-19, in those early months, when we really didn't know what we were facing, it would have been much better if scientists had said, this is a novel virus. We are facing something unknown here. We are doing our best. We are working as hard as we can. We are working around the clock to try to figure out what this thing is and to figure out the best response. And as soon as we know, we will tell you. We will tell governments, we will tell people. We will be out there with the best possible information we can as soon as we can. But right now, we just have to ask you to be patient. I think that if scientists had done that, people would have understood. People understand what it is to face a new challenge. And then when the scientific community did start to understand what we were looking at and did start to understand that actually masking would be effective, and then when we had a vaccine that was looking pretty good, to be able to say, okay, we have a vaccine now, and so far the data are looking quite good. I think the scientific community would have had much greater credibility and would not have created this impression of saying contradictory things, which then of course was exploited by the forces of disinformation. So I think, it gets back to the problem of humility, that it's okay to admit when you don't know, and more than that, not only okay, it's actually essential. If you want people to trust you and to believe in what you're doing, you have to be willing to say honestly when you don't know that you don't know, and to ask people for a little bit more patience, a little bit more time. I think if scientists had done that during the COVID-19 pandemic, we would have been in a much better place.
Una delle cose più frustranti che ho letto in questi 2 anni e mezzo di pandemia è stato vedere come un grande studioso della grande influenza subito dopo la Prima Guerra Mondiale avesse studiato cosa era successo in quell'epoca, cosa aveva funzionato e che cosa no, e avesse concluso svariati anni fa che la ricetta per evitare alcuni dei disastri più importanti fosse un certo tipo di comunicazione molto simile a quella che adesso ha ricordato la professoressa Oreskes. Ebbene, era tutto scritto, articoli divulgativi, libri, eccetera, e semplicemente non abbiamo imparato da quello che avevamo imparato in precedenza studiando un'esperienza simile come la grande influenza pandemica dell'inizio del Novecento. La parola ancora per la penultima domanda, poi ancora una domanda al signore qua davanti e concludiamo. Prego.
La ringrazio, professoressa, della sua bella lezione. Ho letto con interesse già in passato il suo libro, che utilizzo anche a lezione, insomma lo trovo molto, molto chiaro, molto utile anche con gli studenti e le studentesse. Volevo appunto chiederle questo. Secondo lei può avere, come dire, un ruolo cioè nei fenomeni, come dire, di sfiducia nella scienza anche un sentimento, un'emozione come la paura? Nel caso appunto del Covid, per esempio, tra sto appunto pensando alle persone comuni, no? Che magari non avevano, come dire, conoscenza scientifica di cosa fosse il metodo scientifico. Gran parte della sfiducia magari era fortemente anche legata a un sentimento, come dire, di paura. E in molti casi, sebbene ci sia stata anche molta disinformazione, cercare di spiegare loro come appunto il metodo scientifico funziona non è stato in molti casi sufficiente. Quindi volevo appunto sapere il suo punto di vista su questo. Grazie.
Thank you. And thank you so much for kind words about my books, and I'm glad that you're able to use them with your students. Well, fear is very important. Emotions are very important. And one of the things we know from research in communications, from the experience of people in marketing, advertising, Hollywood, that most people, when they make decisions, it's not that they ignore facts completely. People do pay attention to information, but they also pay attention to how they feel about it. And our decision-making processes are some complicated nexus of what we know in our heads and what we feel in our heart. And when we ignore the emotional components of these things, we tend to be ineffective as communicators. And if you don't believe that, all you have to do is watch television, watch advertisements. Most advertisements do not give you a list. If you think about an advertisement for a car, they don't give you a list of all the features of the car. They show you something beautiful and shiny, and they give you the impression that if you drive this car, you will feel good. You'll get to go to a beautiful place. Maybe a beautiful woman will drive with you, right? These are all appealing to emotions. So people who sell things know that emotions are an incredibly important part of persuasion. But in the scientific community, we disdain that. We think that rationality requires us to suppress our emotional responses. And I think that's all wrong. I think it's one of the biggest conceptual errors that people make in science. It's perfectly possible to connect to people on an emotional level, and I don't use the word appeal to emotions because that's often viewed as pejorative, but to connect to people on a human level and then use that connection to communicate information. And that is what I try to do in my own work. I was lucky many, many years ago when I was an assistant professor. I had the good luck to work with a communications professor, and we all came into the room, and the first thing she said to us on the first day is, what is the most important thing for you as a communicator? And lots of the professors said, oh, but I really know my stuff, right? That I'm really prepared. And she said, no, the most important thing is people like you. And that was very stunning to all of us. We didn't think it was about being liked. We thought it was about being experts, knowing our stuff. And I've come to realize over the years that she was completely right. If people don't like you, they won't want to listen to you. If they think you're arrogant, if they think you're obnoxious, superior, condescending, they'll turn off. And unfortunately, many scientists do come across as superior, arrogant, and condescending. So the trick really is to figure out ways to communicate what you know, because as experts, we do know a lot of stuff, but to do it in a way that is compassionate and inviting, to bring people into the conversation rather than to make people feel excluded.
Lei ha parlato dell'importanza di valutare nel momento in cui si ragiona sull'attendibilità di alcuni risultati scientifici. Lei ha parlato di quanto sia importante guardare ai risultati, all'evidence riguardante appunto quello che si sta considerando. Nelle campagne che sono state fatte, che vengono fatte nel cercare di contrastare la disinformazione, spesso, nella stragrande maggioranza dei casi si presentano i dati cercando di far capire che i dati sono attendibili. Ma questo può portare molto spesso al fatto che che le persone non credano più nei dati, forse in parte probabilmente per la sensazione che gli scienziati possano mentire coi dati, possano farli girare a loro favore alla fine. Cosa crede lei? Crede nell'importanza di non solo spiegare i dati, presentare i dati, ma insegnare i metodi con cui la scienza lavora, la ricerca funziona? Crede che questo possa giocare un ruolo importante nella campagna contro la disinformazione? Grazie.
Yeah, absolutely. And of course, the whole point of my book is to really have a deeper conversation about scientific methods, how science works, and why we do sometimes make mistakes and go wrong. And I think to the extent that we can discuss that openly with people, it does create a basis for increased trust because we're being honest. We're being honest about the limits of the activity. I would just maybe say one thing in response to your question, though, when you say, you know, people don't believe evidence or people don't believe data. I'm not sure if that's quite how you put it, but where's that effect? It's also important for us to recognize that actually public opinion polls show that the majority of people in most countries still do believe in science. They still do value the importance of scientific data. We don't have a lot of really good public opinion polling on this question. My postdoctoral fellow, Victoria Colonia, is about to launch a big study in, I think we have 62 countries now, where we're going to try to look in greater detail about what people really do think about science and what are the conditions under which people trust scientific evidence and what are the conditions under which they don't. And so with better data, with better evidence, I think we'll be in a better position, let's say a year or two from now, to be able to answer the questions about what kinds of communication will work to build what I would call warranted trust in scientific findings. So hopefully we'll have those data in 2 years. Victoria is Italian, she's from Bolzano, so maybe in 2 years' time you can invite us both back and we can have some kind of meeting about that, because I think it's a very important question and we're doing what we can to try to get more information to help answer it.
Perfetto, ringraziamo la professoressa Oreskes sia per la sua lezione sia per il tempo che ci ha dedicato a rispondere alle domande e speriamo di averla con noi in presenza nel 2024 e grazie a tutti voi di aver partecipato.